I just told you, if I have an expression, something like where I'm adding the product term, then we can call them the sum of the product term. Okay. So let us try to understand what is the meaning of these things. Okay. Suppose I have a function f that is, let us assume ab plus, let us assume anything, a bar b bar. For example, I have a function something like ab plus a bar b bar. Let us try to make the truth table of this one. Okay. So suppose I have a, I have a b, and I have the function f. And if we try to make the truth table of this one, can anyone tell me what? Yeah, let me write the all the possible inputs. So we have a 4 possibilities: 0, 0, 0, 1, 1, 0, and 1, 1. Can anyone tell me what will be the f for all the cases?
1.
For first, it will be what?
Yes,
0,
sir.
0. If a and b is equal to 0, what I will get?
So 1.
Okay, you will get 1. Okay. So let us assume, yeah, so 0 and 0, that will give you the 0, and a bar dot a bar b bar, like here I will, a will become 1 and b will also become, so I will get function 1. What about the second one?
0.
0.
What about third?
0.
0. What about fourth?
1.
1.
1. Okay, so we are getting something like this one, and this is simply the expression of XOR gate, right? This is the expression of XOR gate. See here, if you see this expression, in this expression, whatever we have, like ab plus a bar b bar, and if you see, this term is nothing but, this is giving, yeah, let me change the color so that you will be interested to understand. So see here, if you see here, where I am getting the function 1, if a and b both are 0, then I am getting the function 1. So this function is nothing but, means 0 means the complement, and where a logic 1 is like output is 1, that min term will be applicable only. So if you see here, here I have a bar and b bar term. So this term indicates a bar, b bar. Okay. Second term, if you see here, this is high, this function is high, so I need to consider a and b here. So the first term indicates a bar b, and the last term indicates ab. And if we try to combine all these things, I'm getting, so the terms which we just got here, these terms are nothing but, these are the min terms. Okay, these are the min terms. And one more thing, this is really very important. One more thing, if I have a function, any other function ab plus a bar b, and if in that function, for all the min terms or the max term, if all the variables are present, then we can call them the canonical form. Let me repeat it again what I am saying. To represent any sum of the product, you can have a two form. One form could be like the canonical form, and the second form could be like minimal form or the standard POS SOP form. Okay, I will tell you in more detail. So if you see this function, whatever we have here, f, this f has all the variables which is required. A and b, I have two variables, and in all the min terms, both are present. So I can call this form is the canonical form. Okay, so if all the variables are present, then we can call them the canonical form. Suppose I have a function something like this. Let us assume I have one function f is equal to a plus b bar c. Okay, if you see here, in the first term, if I see here, I have three different variables, variable a, b, and c. But in the first term, I have only a. In the second term, I have only B and C. So in first term, B and C is absent, and in the second term, A is absent. So I cannot say this function is in the canonical form. So if the expressions are something like that, these kind of functions are this kind of form, we call them the minimal form or the standard SOP form. Okay, so let me write somewhere here in there. We can call them the minimal form or standard SOP form. Okay, so this is the importance that we should understand. Yes, because I'm saying this, sometimes in GATE examination the questions may be in the form of canonical, and maybe some questions are in the form of standard or minimum form. So they may ask like how many variables we have, how much canonical forms or min terms we can implement. So this is like canonical form and the minimal form. These kind of terms are very repetitive. These kind of terms are available in the question papers. So you should know the difference between these two things. Okay, so this is the importance, or this is the difference between minimal form and the canonical form. Now, suppose if I'm talking about the sum of the product, okay, sum of the product form. So what we can do? Suppose I just told you, if I have A and B both are 0, 0, so I am representing it as a bar, B bar. If A is equal to 0 and B is equal to 1, so I will represent this term as if this function is also 1. So in that case, I will represent this as a bar into B. Similarly, for the third one, if I have A is equal to 1, B is equal to 0, so I will represent it as A into B bar, and the fourth one will be represented as A and B. Okay, so let us try to see what is the meaning of all these things. Okay, so let us try to make one table. If you talk about the a 2-bit number, if I have a 2 variables, so in 2 variables, the total possible combinations are 4. Okay, 0, 0, 0, 1, 1, 0, and 1, 1. Okay, whatever we just write here. Okay, and if we convert this into the decimal form, so the maximum number will be like 0, 1, 2, and 3. So we can represent up to 3 if we have only 2 variables. Okay, so let us try to write that thing and try to understand what is the meaning of min term. Okay, so suppose if I have a 2-bit, so I have only 4 possibilities: 0, 1, 2, and 3. Okay, if 0 is there, so what it means, A and B both are 0. Okay, if A and B both are 0, means we can write it like A bar, B bar. This represents A bar, B bar. One decimal equivalent that represents like A bar, B. 2 indicates A bar, A and B bar. And 3 indicates A, B. Okay, so if both the variables in any of these min term is in the complementary form, we can call it min term 0. So we can call this as a min term 0, and this is represented with the small m. If I have A bar B, we can call them min term 1, we can call them min term 2, and similarly min term 3. So this is important to understand the concept of min term, where I have to consider the min term and what will be which of the min term that I have to consider. Okay, so this is important. Decimal equivalent, expression, and the min term. Okay, this is important. Now, how to represent any function in terms of min term? This is also important. Yes, so suppose if you see here, this function is nothing but this is AB plus A bar, B bar. So here we have two functions or 2 min terms that are present, min term 0 and the min term 3. Okay, if you compare this table with the truth table, you can see min term 0 and the min term 3 is present. But how to represent these things? Okay, so to represent any of the function in the sum of the product form or SOP form, I need to write like this. How to write like this? So that is represented as f function and we have a two variable which is a and b is equal to, because we are summing the min terms here, so we need to write the summation here. Okay, and if you see, here, if you see this expression, whatever I have written here, this expression has m0 and m3, so I need to write m0 comma 3. So this function is same as whatever we have written here. Either you can write f is equal to ab plus a bar b, or you can write f ab is equal to summation of min term 0 and 3. So both are true. There is no problem with these things. Okay, so this is how you can represent any function something like this. Any doubt? Do you have anyone? Do you have any doubt? You can ask the questions. So this is how you can represent the function. So this function is same as this one. Okay, so this is how it is important. Suppose I have three variables. Suppose I have a function something like that. Let us try to consider some example. Okay, suppose example. Okay. Suppose I have a function which is a, b, and c, and the expression is given something like summation of min term. Let us assume 0, 2, 4, and 5. Okay, so let us assume I have expression something like that. ABC is equal to summation of m0, 2, 4, and 5. What does it mean? It means that 0 is present, min term 0 is present, min term 2 is present, min term 4 is present, and min term 5 is present. Okay, so if you try to calculate the equivalent binary or equivalent function, how we can represent this function? So can anyone tell me what will be the final function if I want to write in the canonical form? What will be the function? Can anyone tell me? If I want to write this in terms of the canonical form, what will be the function? See, 0 means a bar b, like a bar, b bar, c bar, right? I have to make the equivalent function, something like that. So all the, like I have a three variables, a, b, and c, and for 0 I need to make all three things 0, 0, 0. So I will require a bar, b bar, and c bar. So this is the first term which is related to 0. Now what about 2?
A bar, B, C bar.
A bar, B, C bar. Perfect, because weight of the second digit is 2 to the power 1. Weight of this one is 2 to the power 0, and weight of this is 2 to the power 2. Okay, so A bar, B, C bar. Now if I have to calculate for 4, then what will be the min term?
A, B bar, C bar.
A, B bar, C bar. Perfect. What about this 5?
A, B bar, C.
A, B bar, C. Absolutely correct. So this is how we can calculate, like in terms of the sum of the min term form or in terms of the canonical form. So this is how we can represent, or we can convert one from each other. Okay, so the same function can be written like this. So we were discussing like the SOP form. Then let us talk about how this product of sum is different than the SOP. Okay, so suppose I have two variables, A and B. Let us assume I have A, I have output B, and let us assume I have A and B are both are the input, and let us assume Y is the output. Okay, we can have 4 combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so if I have these 4 combinations for A and B, in that case, let us assume I am getting the output something like 0, 1, 0, 1. Our circuit is designed in such a way that I am getting 0, 1, 0, 1. Okay, so let us try to see how that can be represented in the max term form. See, I just told you we are considering the min term if we are adding the product term, and we'll say the max term if we are multiplying the sum terms. Okay, so because we are talking about the product of sum, so I will consider the max term. Okay, so the max term will be considered. Now if I can write the equivalent decimal, like suppose if 0 0 is there, 0 1 is there, 1 0 is there, and 1 1 is there, so equivalent decimal that could be like, yeah, so let me write something. So equivalent decimal could be like 0 1 2 and 3 if it is in the binary kind of. So 0 0 will be give 0, 0 1 will be 1, 1 0 will be 2, and 1 1 will be 3. Okay, so this is what the decimal equivalent will look like. Now if I talk about, if you can go to the previous slide, in the previous slide, the logic which was high, we were considering this is the product term, and that product term was decided whether what was the content of A and B. If A is equal to 0, I will consider it as a A complement, and if B is 0, I will consider it a B complement. And because I'm talking about the SOP, so I will multiply A complement into B complement. So this is how we can represent it. So similar kind of concept, let us try to use on the second kind of representation, which is the POS. What I have to do here, if A is equal to 1 and B is equal to 1, that this will not be the complement. If we can see in the previous one, previously we used to write A complement for 0. But if I'm talking about the POS form, in the POS form, I need to write it like A. If 0, then I have to write A, and if 1, I have to write it as A complement. This is the first thing. Okay, here A complement. Second thing is, only those max term will be considered where I am getting output logically low, not logically high. Previously, we were considering those min terms where I was getting output was high. Here, I need to consider those outputs where I am getting logically low output. Okay, so by considering these two these things, let us try to do something. Okay, so let me write few things like what is the max term and what is the other thing. So this particular 0 0 combination that represents A plus B. 0 1 combination that represents A plus B bar. 1 0 that represents A bar plus B, and 1 1 represents A bar plus B bar. Okay, so this is first thing. Second thing, I just told you, like if I talk about, yeah, this is simple representation, and if I talk about the max term, okay, so the max term will be capital M0, capital M1, capital M2, and capital M3. For min term, small m is used, and here I need to use the capital M. Okay, so this is how the max term we can represent. So yeah, so if you can see here, it is just like that what we are discussing, but in the complementary kind of thing. Okay, so this is A, B, all these are the variable. Okay, and this is how we can represent the SOP form. Now let us try to see what are the different things that are utilized to represent. Okay, so okay, so this is done. Now if suppose I have any function having this kind of truth table, so which of this component will be represented? Can anyone tell me what is the function, output function of this truth table? What is the output function of this truth table? Can anyone tell me? What is the output function of this truth table? Based on this understanding, this discussion, what is the output function? Anyone?
A plus B into A bar plus B.
A plus B into A bar plus B. Perfect. Absolutely correct. Because I just told you I have to consider only those variables having the output is logically low. Okay, so we have only two combination here which are giving output low. One is this one and the second one is this one. Okay, so these are the two combinations where we are getting the output logically low. Okay, so we will consider only a plus b and a bar plus b. Now the important thing is, yeah, so this is what I can write. So a plus b into a bar plus b. If I have to represent, so if you see here, this representation, we can call it is in the canonical form. Why it is in the canonical form? Because we have two variables a and b, and all the variables are present in both the max terms. So this is the max term, this is the max term, and both the variables are present here. So we can call it, this representation is in the canonical form. Okay, so this is in the canonical form. Okay, similarly, suppose if I have to write in terms of the mixed term and other things, then how we can write? So let us try to represent the same function in different way. So the same function can be represented in a different way, something like f ab. This is equal to, because previously we were doing sum of product. So at the end, what we are doing? We are adding the product terms. Here, if you see, here we are finding the product of some term. Okay, so to represent the POS form, we need to utilize the pi kind of symbol. Pi symbol is used. Okay, pi symbol is used for this purpose, and capital M is used because we are considering the max term. And if you see here, a plus b indicate 0 and 2, like here a plus b is nothing but this is 0, and a bar plus b indicates 2. So this is how we can represent in this way. Okay, so this is a simple representation of this truth table, whatever we have. Okay, one very important thing. Okay, whatever the function we have written over here, this function is nothing but, if you see, this particular function indicates m0 plus m2. What we are doing? M0 plus m2. Okay, we are just simply adding m0 plus m2. Now, if you can consider the sum of the product form, there what I have to consider? I have to consider where I was getting output 1. So output 1 and 1 here. And this is nothing but, this is, if I talk about, this is the m1, small m1, and this is small m3. Okay, so this m0 plus m2 can be written as m1 dot m3. Why? Because here we are finding the product product of sum, and in the previous case we were getting something. I did some mistake. Yeah, I think I did mistake. We are finding the product term. Yeah, product and summation should be here. Okay, so here m0 dot m2 is same as m1 plus m3. Okay, so the same function can be represented like this. Okay, so suppose some of the function or some of the function is given in the POS form, and you have to convert into the SOP form. Then what you have to do? First, you have to convert your function into the canonical form, so that you will get all the min term or max term as per the requirement, and whatever the min terms are present, you can convert that into the max term, and vice versa. Let me repeat it again what I'm saying. Suppose you have a function which is written like this. Let us assume you have a function which is f is equal to, let us assume a into a bar plus b. Okay, this particular function is not in the canonical form, because here I have one max term, Here I have the second max term, and both the max term does not have both the all the variables. Okay, so this kind of form we can call it is the minimal form. So this is the minimal form or standard form, standard POS form. So suppose if I have to convert any of the function which is written like which is in the standard form, and I have to convert into the other form, like this is nothing but this is the POS form. And if I have to convert this POS form into the SOP form, then what I have to do? First step, I have to convert this standard form into the canonical form, so that I will get all the variables, and accordingly I can find which of the maximums are present. Okay. So first step, I have to convert this standard POS into the canonical form. Second step, I have to find what are the max term or the min terms that are present in that function. Once we are ready with the max term or the min term based on the function, we can convert into the opposite one. If minimum is min term is there, then we can convert into the max term and vice versa. So these are some of the steps. Now the question is, how to, like, the second thing can be done, like if you see here, if I have three variables, okay, let us assume I have three variables, so the total possible combinations are a. Okay, so min terms will be from m0 to m7, and max term will be from m0 to m8 m7. Okay, so these are the mixed term, min term and max term limits. Okay, so this is easily doable, but the thing is how this standard form can be converted into the canonical form. So let me tell you how to do that. Okay, so I will explain you in a little bit later on. Okay, so we can do it later on, but these things can be done. Okay? So these are some of the things which are important, especially if we are talking about the POS form. Okay, is there any doubt on the POS and the SOP? Anyone? If you have any doubt, you can ask the questions. Otherwise, we can move ahead with how we can convert the standard form into the canonical form. Okay, so we can check that one. Yeah, let me explain that thing. It's not that much difficult. Let us assume I have a function which is written like a plus a bar b. Okay, suppose I have a function something like this. This function is nothing but this is in the standard form, standard SOP form. Okay, this is in the standard SOP form. Now, if I have to convert this function into the canonical form, then how it can be done? Okay, so let us try to do that. If you see here, in this first min term, I have only one variable. In the second min term, I have the two variables. So if you see in the first variable, in the first min term, I have one variable is missing. Okay, so what we can do? We can write something like this: a into b plus b bar. There will be no impact after this, right? So we can write ab plus like a b plus b bar, and then we will have a bar into b. If we extend this one, then I will get ab plus ab bar plus a bar b. Okay, so this is what I am getting. AB is equivalent to M3, AB bar is equivalent to M2, A bar B is equivalent to M1. So if I have anything which is written like any function which is M1 plus M2 plus M3 is same as capital M0. This is what I wanted to say. Is there any doubt what I am saying? Okay, so this is how we can convert the standard form into the canonical form. Okay, so this is easily doable, right? So you can do it. It's not a problem. Okay, so let us move ahead with the other things. Okay. I'm hoping there is no doubt on this, right? Now, we need to know something about the, suppose just now we discussed about how to represent any function, how to minimize those things, how we can design any circuit or logical circuit based on the functions whatever it provided. Okay, so let us consider I have any digital circuit. Okay, so I have a black box, something like this. Okay, I have a digital circuit having some inputs. Okay, so let us assume I have a n number of input in this digital circuit, and I'm getting some output function. Let us assume I'm getting output function f. Okay, so what does it means? If I have any if I have any digital circuit, if and there are n number of inputs, in that case the total possibilities, total possible logical possibilities could be 2 to the power n. Suppose I have any circuit having 2 inputs. Okay, 2 inputs, then total possibility will be 2 to the power 2, that will be 4. If I have 3 input, then total possibility will be 8. So this is how we can calculate what is the total number of possibilities. Okay, but this is what I can observe or what you understand as of now, but this is somewhat not true. There is some difference. Okay, let me repeat it again what I'm saying. Suppose I have any digital circuit having n inputs, and if I have n inputs, so just we know that in digital system, if I have n inputs, so we can get total possibilities like 2 to the power n. So this is the total possibilities in the input that we can provide. Okay, and based on that, f can be calculated. Okay, yeah, sometimes it is true, but in reality it is not true. This is not the maximum. This is some subset of the all possible combination. This is not the all combinations. Let me repeat it again what I am saying. Whatever the formula we have written here, total possible combinations are 2 to the power 1. This indicates some of the possibilities that we can validate any digital circuit, but this is not all possible combination. Okay, so what is the all possible combination in any other digital circuit? All possible combinations, this is the key point that I want to explain you. The total possible combination with n input logic circuit is equal to 2 to the power n. This looks like very strange. Okay, but this is true. I will tell you how. Okay, so and this is really very important formula. You should remember, you should know this formula. So the total possible combination or the maximum possible combination with n input logical circuit is 2 to the power n. So if I have 2 input, so for 2 input I need to get 2 to the power 2 possible combination, or 2 to the power 4 means that will give you 16 possible combinations. Okay, so not so based on this formula we got to know that we have only 4 possible combination, which is not correct. We will have a 16 maximum possible combinations if I have 2 inputs. This looks like strange, but I will definitely justify this statement how this is true. Okay, before I explain these things, I need to explain. I need to just highlight one more key point. The maximum possible minterms and the maxterm for n input logic is nothing but this is the what we have just explained. So whatever the formula we were discussing here, like 2 to the power n possibilities are there, this indicates how many maxterm and the minterms are possible in any of the digital logic circuit if I have n number of input. It does not represent how many total possible combinations are possible. Okay, so this is the difference between these two things. Now let me try to validate this statement. Okay, so suppose I have an inverter circuit. Okay, so for any inverter circuit, how many total possible combination could be there? Can anyone tell me? For inverter, maximum possible combination, like what we can expect. Don't consider this point. Okay, what you know, we have only 2 possibilities, either 0 and 1, right? So we can have, like, suppose I have a inverter circuit. Okay. So, and if I have an input A and output F, then I can have two possibilities, A or A bar. Okay. So I have only these two possibilities. But based on this formula, what we wrote here, the total input, the total possible combination, that could be 2 to the power 2 to the power 1, means it is giving 4 possibilities. So we know, like, A and A bar is one of the possible, like two possibilities. So what other two possibilities are? So other two possibilities are, if I, so see here, A and A bar, these two are the logical values. Remember, these two are logical value. It is not confirmed that A will always be 0 or A bar will always be 1. If A is equal to 0, then A is fine and A complement will become 1. If A is equal to 1, then A complement will become 0. Okay, so we cannot say that A is always high and A bar is always low. Okay, so A and A bar are the two possible combinations, and other two possible combinations are, if I connect this input to the grounded, or I connect it to the 0, then this is one of the possible combination. This is also acting as an input. Okay, here A and B are the logical input, that can be 0 or 1. This is one of the possibility. But if I directly connect to the ground, then that will also consider as a input. This is the third possibility. And the fourth possibility could be, like, if I directly connect the input with the VDD, then this is the fourth combination. So that for any inverter, the total possible combination, that could be A bar, and 0 and 1. These are the total possible combination for any inverter. Do you have any doubt on this, on inverter? If you have any doubt, please ask. I will repeat it again before moving ahead. Okay, and this is the justification of this first key point. And second key point, you know this, right? Okay, hope you know, you understand the things what I am saying. Okay, similarly, suppose I have a two input logic. For example, I have a two input logic. Let us assume I have a AND gate. Okay, so what are the possibilities? Possibilities could be, like, let us assume A and B is there. Okay, so it could be like A bar, B bar, A bar, B, A, B bar, and A, B. These are the four possible combinations which we already know. Next possible combination could be, keep it to the VDD, means logic 1. So 1 into B is the next possibility. 1 into B bar is another possibility. Now I can keep it 0. So 0 into B is one of the possibility. 1 into B is 0 into B bar is another possibility. Similarly, you can do it for A. 1 into A is one of the possibility. 1 into A bar is another possibility. 0 into A is one of the possibility. 0 into A bar another possibility. 1 into 1 is one of the possibility. 1 into 0, 0 into 1, and 0 into 0. These are the possibility. So you can find all the possible combinations, and you can check it out how many possible combinations we can accommodate. Okay, so other combinations we know that A bar, B bar, A bar, B, AB bar, and AB. So if you count here, we are getting total 16 possible combinations if I have two inputs. Okay, so similarly, you can calculate the inputs, total number of possible combinations. So this is what you know. Yeah, why I am putting too much stress on this formula? Because in GATE examinations, some of the tricky questions may come like this. Okay, I saw many times the questions are related to this formula, and people generally they know this formula to the power n, and they do mistakes. Okay, so for that you should know this is the correct formula, 2 to the power n. Okay, fine. Let us move ahead further. Is there any doubt? Anyone? If you have any doubt, you can ask the questions. Fine. Now, one very important thing is, what is the advantage of minimization? Like, yeah, we already saw before. Suppose I have any function, and if I'm implementing that function based on the logical gate, this is easily doable. It is not a problem. But if I'm minimizing that function, then there are certain advantages. Okay, what are those advantages? Let us try to see. First advantage is number of logical gates. These are reduces. Okay, so the number of logical gates reduces if I'm minimizing the function. Okay, second advantage that could be speed. Speed means what? Suppose I have a logical circuit. Let us assume I'm making a circuit something like this, which I think which we saw in the previous class. We had a circuit something like this, and after minimizing, I was getting output is always 1. Okay, this is what we saw in the previous class. Okay, so if you see here, all the logical gate has their own delay. So let us assume the delay of the first stage gate is T1, and because this second stage gate depends on the output of first stage gate. Okay, so the first stage gates will take, let us assume, T1 time, and the second stage gate is they are taking T2 time. So the total time required to get the output is T1 plus T2. So this is the minimum time required to get the output if I have the logical gates that are connected. But if I will minimize it, so I saw here there is no logical gate involved. Directly VDD will be transferred, so delay is close to 0. Similarly, might be if initially there was 3 stages, and after minimization, if it becomes only 2 stages, so the delay will be reduced. So that is why I am saying the speed of getting output will be faster, or the speed will be increased. Okay. Third advantage of minimization is the power dissipation. Okay, let us try to see. Suppose initially I had a 3 logical gate that are used to implement any function, and after minimization, let us assume I need only 2 logical gates. So each logical gate can have their own power dissipation. Okay, so the total power dissipation will be added. Okay, and if we have less number of logical gates, then the total power dissipation will be less. So the power dissipation is going to reduce if you are considering the minimization. Okay, so this is important. Now, one more advantage of minimization is number of functions per unit area. That is also going to reduce, because initially I need more number of gate to implement same function, but after minimization we required less number of logical gates to implement the same function. So what it means it required less area to implement the same function. Okay, so the number of functions per unit area, that is also going to increase. We can accommodate more number of functions in that particular area. Okay, next advantage is the cost. Yeah, cost, like, see, if you can accommodate more number of logical gate in a small area, so you can implement more number of functions. So the overall cost of design, that will reduce. Okay, the cost of design will reduce. And also, like, because the last one is the complexity will also reduce, because see here, initially I need 3 gates, and after minimizing we need less number of gates. So the complexity is directly proportional to the number of gate requirement. Okay, so if number of gate requirement is less, complexity will be reduced. Okay, so this is one of the advantages. So this is really very important to minimize the Boolean function with minimum number of min term or max term. So that will give you some benefit. Okay, and these are some of the benefit which we will get after minimizing the things. Okay, now let us try to take some example. Yeah, we took one example yesterday, but let us take one more example. Let us try to solve some question. Let us assume I have a function which is like a plus b into a plus c. Let us assume I have this function. if you see here, this function is nothing but this is given in the POS form. This is in the POS form. And if you see how many gates are needed, can anyone tell me? If I want to implement this function, how many logical gates are needed and which logic gate is required?
Sir, 3.
3 logical gate. Which one?
Sir, 2 OR gate and 1 AND gate.
2 OR gate and 1 gate. Perfect. Absolutely correct. Okay. So see here, for A plus C, we need 1 OR gate. For A plus B, we need 1 OR gate. And to multiply these two things, we need 1 AND gate. So we need 3 logic gates, 2 OR and 1 AND gate is required. Now let us try to minimize it. Okay. So if I have to minimize it, let us try to expand this one. So if I expand it, how it will look like? Yeah, you can directly apply the formula which we have already studied before. That will become like A plus B into A plus C. Like A is common in both, so A will become like A, and B and C is here, so B plus C can be written. So A plus BC will come out. Okay, this is the formula whatever we have already studied. But how we can prove this one? Okay, so let us try to see. If we can expand this one, so that will become A into A plus A into C plus A into B plus B into C. A into A, this is nothing but this is A. Okay, and if you see here, if we can take out the A as like, see here, this will become like simply, yeah, let me write it perfectly. A plus AC plus AB plus BC. If you take A common, so that will become 1 plus C plus B plus BC. Okay, and if you know that if we are adding anything with 1, that will also always become 1. So this term will become 1. So this becomes A plus BC. Okay, so this is how you can prove it. Now if you see at this point, how many logical gates you need? You need 1 logical gate for this one, for BC, and 1 for this one. Okay, so you need only 2 logical gates, 1 AND gate and 1 OR gate. Okay, so this is the requirement. So the total number of gate requirement is reduced after minimizing, and this is nothing but this is in the POS form, SOP form. Okay. Sometimes, this is really very important. Suppose if there is any function, right, and that function required more number of gate, this function can either be in the POS form or it can be in the SOP form. Okay, if you are changing from POS to SOP, might be the number of gate requirement will be reduced. This is really very important what I am saying. Let me repeat it again. Suppose if there is a function, any function is represented in the POS form. Okay, and let us assume the gate requirement is more in the POS form, and if I will convert that POS into the SOP, might be the number of gate requirement will be reduced. How and why? Let me go back to the previous slide, and you will be happy to know that we have already done this part. How we have done this part? Let us see. See here. If you see this formula or this final expression, if you see, the same function can be represented with the help of 3 minterms, or the same function can be represented with the help of 1 max term. Okay, so if you are writing the function in terms of minterm, then you require more number of gates to implement that function. But if you are writing in terms of max term, you will require less number of logical gates. Okay, so this is really important. Why we need conversion from one form to another form? Why POS to SOP and SOP to POS conversion is required. So this is the reason why we need to convert one form to another one. Okay, so this is how we can decide these things. Is there any doubt what I said? This is really important important point that you should remember, and some logical kind of questions may come in the GATE examination related to this one. So they may ask, like, they will give one function that will be in the SOP form, for example, and now they will ask how many min terms are there. Means how many minimum logic gates are required. So if you don't know that you have to convert in another form to minimize the number of gates, so you will simply calculate based on whatever expression is given, and that will become the incorrect answer. Okay, so to solve that one, first you need to think whether after converting from one form to another form, whether the number of min term or maximum are reducing or not. If it is reducing, then you need to convert it. It is not mandatory that you will always get minimum number of gates after converting from POS to SOP and vice versa. Suppose you have a function having two min term, let us assume M1 and M2 was there, and we can also write M0 plus M0 into M3. So here we see I had in one side I have two min terms, and another side I have two max terms. So then the possibility number of gates will be equal. Okay, so this is not always true that you will get always less number of logical gates after converting its form. Okay, but yes, you can get it. So this is important. Okay, so yeah, so this is what the advantage of minimization is.